If you've ever wondered how the hidden digital world around us is actually held together, well, you are definitely in the right place.
Before a single email is sent, before a web page even starts to load or a video stream buffers, there is this totally hidden, physical and logical map dictating exactly how our devices communicate. We rarely see it, but it completely governs the speed, the security, and the reliability of our daily digital lives.
So today we're going to step through 5 key areas. First, what network topology actually is. Second, bus and ring setups. Third, star and tree configurations. Fourth, the mighty mesh topology. And finally, combining forces with hybrid topologies. We'll be grading them all on cost, reliability, security, and scalability to see which ones actually survive the real world. Let's get to it.
Section 1. What is network topology? To truly understand our digital foundations, we first need to define the blueprint itself.
Now, what's really interesting here is how we absolutely have to separate the literal cables in your walls from the invisible rules governing the traffic on those cables. At its core, topology is simply the arrangement of nodes or devices in a computer network. But it operates on 2 completely distinct levels. You might physically place 3 nodes on the ground floor and 2 on the first floor, right? That's your physical topology. But the logical topology dictates how the data actually flows from node to node, totally ignoring whether they're in the same room or on different floors. It's essentially the difference between the physical map of the roads and the traffic laws governing the cars on them.
Section 2. Bus and ring topologies. Let's start with the earliest building blocks of networking, where devices are forced to share a single pathway.
Think of this kind of like a public PA system, or even electricity flowing. In a bus topology, all nodes connect to one main backbone cable using little drop cables. If one node wants to send a message to another, it just puts the data onto this common transmission medium. The signal travels in both directions, and every single connected computer receives a copy of that data. The catch? Everyone hears it, but only the intended recipient actually listens to it and accepts the packet. The others just ignore it entirely.
So the crucial point is that while a bus setup is incredibly cheap and easy to put together, which is great for a temporary network, it has some pretty severe flaws. Because everyone receives the broadcasted data, there is absolutely zero privacy or security. And worst of all, it is not fault-tolerant. If a single node breaks, sure, the rest are fine, but if that central backbone cable snaps, the entire network goes down instantly. Add in the fact that data can literally collide if sent at the exact same time, and, well, you can see why it scales so poorly.
To solve that messy collision problem of the bus, engineers came up with the ring topology. Imagine a bus topology, but looped into a closed circle. Here, the network uses a peer-to-peer speaking stick method, kind of like a digital kindergarten circle, called a token. This digital token just circulates continuously. If a computer wants to send data, it actually has to wait its turn, grab the empty token, attach the data, and send it along. The data then flows unidirectionally, usually clockwise, passing through all the intermediate computers until it finally reaches its destination.
Let's look at the report card for the ring. Even though it's fast, completely avoids data collisions, and gives everyone equal access, it still suffers from that dangerous single point of failure. If just one node dies, or one tiny link in the chain breaks, the whole loop is disrupted. Plus, because data has to pass through neighboring computers to reach its final destination, security remains pretty low. And if you want to add a new computer, you literally have to break the ring to splice it in, causing network downtime for everyone.
Section 3. Star and tree topologies. Clearly, relying on a single shared cable or a fragile loop isn't exactly ideal. So let's see what happens when we introduce a centralized boss to manage all this traffic.
Enter the star topology. Instead of nodes talking directly to each other or sharing a communal wire, all point-to-point traffic must pass through a central hub or a switch. This central device acts as the ultimate traffic cop. If node A wants to talk to node B, it sends the data straight to the center, and the center forwards it directly to the destination.
The star topology is incredibly popular, and its high scalability grade tells you exactly why. It is so easy to design and implement. If one node's cable breaks, only that specific node goes offline. The rest of the network just keeps humming along perfectly. But there is a catch. That central device is your new single point of failure. If the hub dies or gets overloaded with traffic, creating a massive bottleneck, the whole network stops. Security is also a bit of a mixed bag here. If your center is just a basic hub, it stupidly broadcasts private messages to everyone. But if you spend a little more on a smart switch, it'll route that data privately to the correct recipient.
And this brilliantly illustrates how we can combine the scalable branches of a star network with the long-distance backbone of a bus network to create a tree topology. Imagine multiple star networks, all connected to a single central bus backbone. It basically forms a hierarchical parent-child relationship between all the nodes.
So the tree topology is highly scalable. If you need to expand a network across a massive building, you just add more branches. It's relatively cheap too, because it uses standard cables. But, and this is a big but, because it borrows from the bus topology, it inherits that fatal flaw. Cut the main trunk, the backbone cable, and all the connected branches go down. It's an awesome compromise for scale, but it still lacks that bulletproof reliability we really want.
Section 4. The mighty mesh topology. Now, what if budget was absolutely no object? What if we eliminated shared cables and central hubs entirely, and just connected every single computer directly to every other computer?
To pull that off, we use the mesh topology. But let's look at the math for a second. Using the mathematical formula of n times n minus 1 divided by 2, well, if you want to connect just 10 devices in a full mesh, you're going to need exactly 45 separate cables. Every single device needs 9 separate ports just to plug in all those wires. No joke.
Because every node has multiple direct paths to its destination, a mesh network is quite literally bulletproof. If one cable gets cut, the data just instantly routes through another path. This makes it 100% fault tolerant. It's also highly secure because communication is point-to-point and dedicated. No one else is sharing that wire, so absolutely no one else can eavesdrop on the data. But, as you can probably imagine, wiring 1,000 computers this way in an office would create a massive, unmanageable spaghetti monster of cables.
So while mesh gets straight A's in security and reliability, it absolutely fails the cost and scalability test for local networks. Adding even a single new device to a 100-node mesh means running 100 brand new cables. It is an administrative nightmare. However, on a massive global scale where physical wires are replaced by huge routing nodes, this decentralized, highly redundant structure is exactly how the internet itself is built.
Section 5. Combining forces, hybrid topology. Finally, let's look at how these building blocks come together in the real world, because it's pretty rare that one single approach solves every problem perfectly.
And that brings us to the hybrid topology. Now, it's absolutely crucial to note that combining two of the same topologies, like just linking two ring networks together, doesn't count as a hybrid. A true hybrid intentionally mixes two or more different architectures. For instance, you might use a star topology for your individual office departments. Connect those departments together via a ring, and then link multiple buildings with a bus backbone.
I think this perfectly captures our main takeaway today. Modern networks do not rely on just one perfect topology. Network design is the ultimate exercise in compromise. By blending the cheap, long-distance reach of a bus, the centralized, easy management of a star, and the robust, fault-tolerant redundancy of a partial mesh, engineers can tailor a network perfectly to the physical constraints and the budget of literally any organization.